When you decide to look inside an atom, something genuinely strange happens, not because the atom is trying to be mysterious, but because your everyday instincts quietly stop working. We're all trained from childhood to believe that things are where they are, that objects follow paths, that causes lead neatly to effects. A ball rolls across the floor, a car stays in its lane. If you don't look at something, it's still there doing its thing. That framework works beautifully for daily life. It keeps bridges standing and coffee cups from floating away. But the moment you shrink your gaze down to the atomic scale, that framework collapses. Inside an atom, particles don't behave like little billiard balls bouncing around in a tiny box. They don't have precise locations in the way we're used to. They don't even move along clean, well-defined paths. Instead, what you find is a set of possibilities, probabilities, a kind of controlled uncertainty. The electron, for example, is not sitting somewhere waiting patiently for you to notice it. It exists as a spread of chances, a cloud of maybe here, maybe there. And the unsettling part is that this isn't a limitation of our instruments or our intelligence. This is not ignorance. This is how nature actually operates. Richard Feynman was very clear about this and refreshingly honest. He didn't dress it up. He didn't try to make it comforting. He said, in effect, if you think you understand what's happening inside an atom, you probably don't. Because understanding, in the usual human sense, depends on intuition. And intuition evolved to help us throw spears and cross rivers, not to comprehend reality at scales billions of times smaller than our eyes can see. Nature is under no obligation to make sense to us. What's really happening here is not that physics becomes complicated, but that our expectations become unreliable. We expect things to have definite properties at all times. We expect motion to be continuous and predictable. We expect reality to exist independently of our descriptions of it. At the atomic level, those expectations fail quietly, consistently, and without apology. The equations still work. The predictions are stunningly accurate, but the mental pictures we rely on fall apart. This is the first psychological shock of modern physics. Not that the universe is chaotic, but that it is precise without being intuitive. It follows rules, but not rules that align with common sense. The atom obeys laws that are mathematically elegant and experimentally verified, yet conceptually uncomfortable. You can calculate exactly how an electron behaves, but you cannot imagine it behaving that way without distorting your everyday sense of reality. And that discomfort matters because it forces a philosophical shift. It tells us something unsettling about knowledge itself. There is a difference between knowing how something works and being able to picture it in your head. Feynman loved this distinction. He warned against the false comfort of mental images that feel right but explain nothing. In atomic physics, the math tells the truth, even when the story we want to tell ourselves breaks down. This is where many people quietly step back. They decide it's too strange, too abstract, too detached from real life. But that reaction misses the point. The atom is not a special case. It is the foundation of everything. Every solid object you've ever touched, every thought you've ever had, every emotion you've ever felt is built on this strange, probability-driven world. The reason the chair doesn't collapse beneath you is not because matter is solid in the way it appears, but because these odd atomic rules are astonishingly consistent. So when reality stops behaving normally inside the atom, it's not telling us that the universe is broken. It's telling us that our sense of normal was never fundamental to begin with. It was a practical shortcut, not a deep truth. And once you see that, something powerful happens. You realize that certainty, the kind we crave, is not the same thing as understanding. The universe is not required to match our mental habits. we are required to adjust ours. Feynman's brilliance was not just in explaining the equations, but in showing us how to live with that uncertainty without surrendering clarity. He didn't ask us to stop asking questions. He asked us to ask better ones, to accept that confusion is not a failure of intelligence, but a sign that we are finally touching something real. If looking inside an atom feels unsettling, that's not a weakness, it's an invitation. An invitation to loosen your grip on certainty, to replace comfort with curiosity, and to remember that the most reliable truths often begin by dismantling what we thought we already knew. Once you accept that the atomic world refuses to behave in the tidy, predictable ways we're used to, a deeper and more unsettling idea comes into view. It isn't just that particles are fuzzy or that their behavior can only be described statistically. It's that the very act of looking, of measuring, of observing, is woven into what actually happens. In everyday life, observation feels passive. You look at a tree and the tree doesn't care. You measure the temperature and the weather doesn't change its mind. But at the quantum level, that assumption quietly fails. This is where people often stumble into confusion, and understandably so. The phrase, "the observer affects reality," gets repeated until it sounds mystical or vague, as if consciousness itself is bending the universe. Feynman hated that kind of sloppy thinking. The truth is both simpler and more profound. Observation means interaction. To measure something at the atomic scale, you must disturb it. You cannot check where an electron is without bumping into it in some way. And that interaction is not a side effect. It is the event. Take the famous double-slit experiment. If you don't try to find out which path a particle takes, you get an interference pattern, as if each particle somehow explores all possibilities at once. The moment you set up a detector to see which path it goes through, that pattern vanishes. The particle behaves differently, not because it knows it's being watched, but because the conditions of the experiment have changed. The measurement reshapes the situation. Nature responds to what is done, not to what is intended. What's psychologically challenging about this is that it breaks the clean separation between the observer and the observed. We like to think of ourselves as standing outside the universe, peeking in like spectators. Quantum physics says that's a useful illusion at large scales, but not a fundamental truth. At the deepest level we can currently probe, you are part of the experiment, not in a poetic sense, but in a physical one. Your tools, your measurements, your attempts to extract information are all active ingredients in the outcome. Feynman's insight here was subtle but relentless. He didn't claim that human awareness creates reality. He claimed something more demanding, that reality does not come with pre-labeled answers waiting to be revealed. The questions you ask and the way you ask them matter. Nature offers probabilities, not certainties, until an interaction forces a specific result. And once that result appears, it's real, measurable, and consistent. There's no magic involved, just a universe that refuses to be pinned down without being touched. This has a philosophical consequence that reaches far beyond physics. It challenges the idea that knowledge is merely the act of uncovering what was already there in a fixed form. Instead, knowledge becomes participatory. You don't just receive facts, you enter into a relationship with the system you're studying. The boundaries blur, objectivity survives, but it becomes more disciplined, more honest. You can still get reliable results, but you must acknowledge the role of the measurement itself. Psychologically, this is uncomfortable because it undermines our craving for absolute detachment. We want clean answers without involvement. We want truths that don't implicate us. Quantum mechanics refuses that comfort. It says, you can know, but not without consequence. You can measure, but not without influence, and that's not a flaw. It's a feature of how reality is structured. What's remarkable is how stable this instability is. Even though outcomes depend on measurement, the statistical patterns are rock solid. The probabilities don't drift or wobble. They follow precise rules that have been confirmed to extraordinary accuracy. So, we're not dealing with chaos or subjectivity. We're dealing with a universe that is deeply lawful, yet fundamentally interactive. Feynman often emphasized that the real lesson is not to ask whether reality is strange, but whether we are willing to accept what experiments are telling us, even when the message clashes with our instincts. The observer effect is not an invitation to mysticism. It's a demand for intellectual humility. It tells us that understanding requires participation, not distance, and that the act of inquiry is itself part of the story. If observation changes the outcome, then attention matters, not just in physics, but in how we approach learning, thinking, and even living. Where you direct your effort shapes what becomes real for you. The universe does not hand you meaning. You help bring it into focus by the way you engage with it. After you come to terms with the fact that observation is not passive, another quiet shock settles in, one that feels almost insulting to common sense. When physicists tell you that atoms are mostly empty space, they're not being poetic. They mean it literally. If you were to scale up an atom to the size of a cathedral, the nucleus would be a tiny speck near the center, and the electrons would be so far away that calling them around the nucleus becomes misleading. Almost everything in between is nothing. No substance, no solidity, just space. And yet here you are, sitting in a chair that does not collapse beneath you. You can knock on a table and feel resistance. You can press your hand against a wall and it pushes back. This creates a profound contradiction between what we feel and what is actually there. The world appears solid, but its fundamental structure is overwhelmingly empty. So the natural question is, if matter is mostly nothing, why does anything feel real at all? Feynman loved this question because it exposes how easily we confuse sensation with structure. The solidity you experience is not due to tiny hard objects packed together like bricks. It comes from interactions, forces. When you press your hand against the table, the electrons in your hand repel the electrons in the table through electromagnetic interaction. They never truly touch in the way your intuition suggests. What you feel as hardness is a balance of forces, not contact between solid things. This realization forces a shift in how we think about reality. We tend to believe that real means tangible, dense, and material. But at the atomic level, reality is defined by relationships, not stuff. The forces between particles are more fundamental than the particles themselves. Matter is not a collection of objects. It's a network of interactions that behave consistently enough to create the illusion of solidity. There's a psychological lesson hiding here. Much of what we treat as fixed and immovable in our lives is more like that table than we realize. It feels solid because the forces are stable, not because it is unchangeable. We mistake resistance for permanence. The atomic world teaches us that stability does not require massiveness. It requires balance. Feynman often pointed out that physics doesn't take sides with intuition. It takes sides with experiment, and experiments tell us that empty space, governed by precise laws, can produce everything from stars to thoughts. Your body, your brain, your memories are arrangements of mostly empty atoms, held together by forces that operate invisibly and relentlessly. There is nothing fragile about this emptiness. On the contrary, it's what makes structure possible. Philosophically, This undermines the idea that meaning or value must be grounded in something heavy or permanent. If the most solid things we know are built on emptiness, then perhaps substance is not the same as significance. Perhaps what matters most is not what things are made of, but how they hold together and how they interact. This perspective also reframes fear. We often fear emptiness, silence, uncertainty, gaps in knowledge, as if they were signs of absence or failure. Physics suggests the opposite. Emptiness is not a void to be avoided. It is the stage on which everything happens. Without space, there are no forces. Without gaps, there are no structures. Without apparent nothingness, there is no something. Feynman's approach was never to romanticize this, but to make it precise. The equations describe exactly how these forces operate, how electrons arrange themselves, how energy flows. The wonder comes not from mystery for its own sake, but from the realization that the ordinary world rests on principles far stranger and more elegant than our senses suggest. When you truly absorb this, it changes how you look at limitation. What feels like an immovable barrier may simply be a stable interaction waiting to be altered. Just as solidity is not absolute at the atomic level, many of the constraints we accept as final are products of balance, not destiny. Change the forces, and the structure changes. So the next time the world feels heavy, dense, and unyielding, remember this: the chair, the wall, even your own body are triumphs of invisible relationships playing out in vast emptiness. Reality is not held together by weight, but by order. And once you see that, you realize that even the most solid things are more flexible than they appear. By the time you reach this point, after watching certainty dissolve, observations step into them. Story and solidity reveal itself as organized emptiness. There's a temptation to ask for closure, a final explanation that makes everything click into place. Feynman would gently disappoint you here, because the last lesson is not about resolution. It's about learning how to live without it. One of his most uncomfortable but honest claims was that no one truly understands quantum mechanics in the way we usually mean understand. Not because it's poorly understood, but because our language and intuition evolved for a different scale of reality. We want clean pictures. Nature gives us reliable predictions instead, and the mistake is thinking that this gap is a temporary failure rather than a permanent feature of being human. This is where accepting mystery becomes an intellectual discipline rather than a surrender. Feynman didn't celebrate confusion for its own sake. He demanded precision. He insisted on clear thinking, rigorous experiments, and mathematical honesty. But he also refused to pretend that clarity must always come with comfort. Some truths are sharp-edged. They cut through our assumptions instead of reinforcing them. Psychologically, this runs against a deep instinct. We equate understanding with control. If we can explain something intuitively, we feel safer around it. If we can't, we feel exposed. Quantum physics offers no such safety net. It says, here is how nature behaves with astonishing consistency. Whether you like the explanation or not is irrelevant. The universe is not confused. We are. There's a quiet maturity in accepting that. It shifts the goal from needing to feel satisfied to wanting to be accurate. It replaces the need for certainty with respect for evidence. Feynman trusted nature more than human opinion, including his own. That's why he was willing to say, "I don't know," without embarrassment. In science, that phrase is not weakness. It's the doorway to progress. Philosophically, this reframes what it means to understand anything at all. Understanding doesn't mean reducing reality to something familiar. It means expanding yourself to accommodate what's true. The universe doesn't owe you intuition. It offers patterns, relationships, and laws. Your task is not to tame them into comfort, but to learn how to think alongside them. This attitude has consequences far beyond physics. In life, we often cling to simplified stories because they feel stable. We resist ambiguity, uncertainty, and contradiction. But the atomic world shows us that stability can coexist with uncertainty, and that reliability does not require simplicity. Nature works even when we don't like the explanation. Feynman's genius was not that he removed mystery, but that he showed how to coexist with it honestly. He didn't hide behind vague language or philosophical fog. He said plainly, the equations work, the predictions are right, and if that bothers you, good. That discomfort is the price of touching something real. Once you internalize this, curiosity changes character. It becomes tougher, more resilient. You stop demanding that ideas reassure you before you take them seriously. You stop confusing familiarity with truth. You learn to hold questions open without rushing to close them just to feel settled. And there's a strange freedom in that. When you stop pretending that understanding must feel intuitive, you become harder to fool, by others and by yourself. You gain the ability to explore without needing guarantees. You can stand in uncertainty without collapsing into confusion. That may be the deepest lesson hidden inside the atom. Reality is not obligated to make sense to you, but it is astonishingly consistent if you are willing to meet it on its own terms. Curiosity, disciplined by humility, turns confusion into progress. So don't wait for the universe to become comfortable before engaging with it. Lean into the mystery, demand honesty from your thinking, and keep asking questions even when the answers refuse to feel familiar, because that's where real understanding begins.